Now that we've talked about position, velocity, and acceleration, we can complete looking at our motion graphs. And we're going to look at two additional motion graphs here. We're going to look at velocity as a function of time, and we're also going to be looking at acceleration as a function of time graphs. In this first one, velocity is a function of time, we're plotting how the motion of the object or the velocity of the object is changing over some particular period of time. Looking at the slopes of this graph, because slope would be change in y over change in x, that'd be change in velocity over change in time. The slopes of a velocity as a function of time graph indicate the acceleration of an object. But there's more to the velocity as a function of time graph than just determining the acceleration. We want to take a look at the shape of the graph itself. If the lines on the graph are completely horizontal, that means the object is undergoing a constant velocity. If you have a slope line, that means that the object itself is changing its velocity over time. If we're just looking at the slopes of the line, if we want to compare acceleration, because acceleration would be the slope of the line, the steeper the line is, the greater the acceleration it's undergoing. The final part of the acceleration under a velocity as a function of time graph is the area under the graph. When we're looking at this, if we have a particular velocity for a period of time, we could always find the position of an object because velocity times time will give us the displacement of the object. If we take the area under a velocity as a function of time graph, we end up getting the displacement for any particular time period in which we take the velocity for. The last graph we're going to look at, and this is more of a rare graph, but we're going to talk about it, is acceleration as a function of time graphs. And here we have time on the x-axis and acceleration on the y-axis. And the only really relevant value that we could discern from this, other than just reading what the accelerations are at particular times, is the area that we would take under the curve. This area of an acceleration as a function of time graph gives us the change in velocity over that time period. Looking at all the graphs as one, because now we've looked at displacement, velocity, and acceleration as a function of time graphs, we can see how each of these graphs have significance in their slopes and in their areas under the curves. For the slopes, a position versus time graph, the slope will give you velocity, and a velocity as a function of time graph will give you acceleration. Notice that for the slopes, it's whatever's plotted on the y-axis divided by whatever's plotted on the x-axis. So position versus time, that would be displacement divided by time. Velocity is displacement divided by time. In a velocity as a function of time graph, our slope, which would be the change in velocity over the change in time, will give us acceleration. If we look at the areas under the curve, it gives us a little bit of a different metric. There's no significant area for position as a function of time, but if we look at velocity, if you're taking the area, it's the same thing as multiplying the axes together. Velocity times time will always give you the displacement, and acceleration times time will give you the change in velocity. Let's go ahead and take a look at an example. This one's not in your notes, but I want to take a look at this example. Here we have the acceleration that's being shown by a velocity as a function of time graph. And in this graph, you can see that we have velocity on our y-axis and time on our x-axis. What we're going to do is we're going to try to determine what the acceleration of this object is. And we know that the acceleration is going to be equal to the slope of this graph, and that the slope of the graph is going to be the change in y-axis over the change in x-axis. So we're going to take a look at the point at 4:2 or 2:4, where we have a time at 2 seconds, gives us a velocity of 4 meters per second, and then we have the origin, which is 0, 0. So we can take our slope, change in y over change in x, or 4 meters per second divided by 2 seconds, gives us an acceleration of 2 meters per second squared. So if we're looking at a velocity as a function of time graph, we can always determine the slope of this graph in order to find what our acceleration is. We can also, for the same exact graph, try to find a displacement. And on this graph, we want to figure out how much displacement has occurred in the first 2 seconds of motion. Now we know that if we're looking at the area under the curve, that the area is equal to displacement. Now this is something that you might not have done, but if you're looking at this graph, what we're going to do is we're going to shade the area between the x-axis and the curve. So you can see right here, we just have the curve on the graph. And then I've colored in blue a geometric shape here. and it's a triangle. So we're going to take a look and try to find the area under the curve here. And if we're trying to find the area of a triangle, it's 1/2 base times height. Our base here is 2 seconds, and our height is 4 meters per second squared. So we're going to calculate the area of this triangle, which is going to be 1/2 base, which is 2 seconds, and height, 4 meters per second. So 1/2 times 4 meters per second times 2 seconds gives us a value of 4 meters. This is how we take areas under the curve in order to find out a value that would be given by that. The next examples in your notes are going to look over at another velocity as a function of time graph. They're going to ask you to take a displacement as well as a acceleration calculation from the slopes in the area. Go ahead and try that. And then when you're set with that, you can start looking at some of the examples that we have in our forums to finish out this module.